Today's topic is Dijkstra algorithm. It is basically used to find out the shortest path possible. For example, if you want to go to a place, there can be several routes. By using Dijkstra, you will be able to find out the shortest path. There are two types of shortest path problems. First, single source shortest path problem, meaning you will be given a single source and you would have to find out the shortest distance from that source to all other vertices. It can be solved using Dijkstra algorithm or Bellman-Ford algorithm. The second one is all pair shortest path problem. You'd have to consider every vertex as the source vertex and find out the shortest distance to all other vertices. And it can be solved using Floyd-Warshall algorithm. Before starting the actual algorithm, let's learn about some basic info. Let's say you have three vertices A, B, and C. A is your given source, and we'd have to find out the distance of C from A, the shortest distance. So at first we can see the direct distance from A to C is 5. So dist of C is equal to 5. But if we take this path, we can say the distance of C is equal to 3 plus 1 equals to 4. So 4 is obviously the smaller one. So the shortest possible distance is 4, right? So let's write down the logic behind this. At first, the direct distance of C was 5. But then we calculated the B via route. So the B via route was distance of C equals to distance of B plus cost of B comma C. Here we wrote cost of B comma C because we will use the dist array when we calculate the distance from the source, meaning A vertex, to any other vertex. So dist of B was 3, cost of B comma C was 1, so equals to 4. And now we'll check if dist of C is greater than dist of B plus cost of B comma C. If this is true, then we will change or update the distance of C to dist of B plus cost of B comma C, because we will always choose the smaller value. We also have a few things to realize. The distance of A to A is always going to be 0. Because if you are already at your destination, then obviously the distance is going to be 0. However, before we connect any path from A to B or A to C, there wasn't a way to reach any destination from A. That would mean the distance from A to any other vertices at first will always be infinity. After we establish any path, we can say that we have a distance which might be 4 or 5 or 6. But before we established any path, the distance was infinity. To maintain the shortest distance, we are going to use an array named dist. So in the dist array, for source vertex, the distance will be 0, and for all other vertices, the distance will be infinity at first. Then we will later on update the distance as we progress. We'll also have a table named list of vertices. In it, we'll store pairs. The first integer will point to the vertex, and the second integer will point to the distance from the source. At first, in the list of visited vertices, the source will be added with its distance. So 0, 0, and we will choose this as the source. Now the adjacent vertices of 0 are 1 and 4, and the distance of 1 is 4 and the distance of 4 is 8. Between these two, 1, 4 is smaller since the distance is smaller. So we'll choose this as our next source. So 1, 4. The distance of the new source will never be updated again since we already chose the smaller value. So in the dist array, now we'll change the distance of 1 to be 4. And the adjacent vertices of 1 is 2 and 4. So the distance of 2 will be 4 plus 1 equals to 5. So 5. And let's calculate the distance of 4 via 1. So 4 plus 2 is equal to 6. Since 6 is smaller than 8, we'll update the value of 4. So 4, 6 will be the new distance. Now between these two, 2, 5 is smaller, so we'll choose this as our next source. So 2, 5, and we'll update the distance of 2 in the dist array. So 5. From 2 we can go to vertex 3, 6 and 8. So for 3, distance will be 5 plus 7 equals to 12. So 3, 12. For 6, the distance will be 5 plus 6 is equals to 11. So 6, 11. For 8, distance will be 5 plus 2 is equal to 7. So 8, 7. And previously 4, 6 was left out. So 4, 6. So among all of these, 4, 6 is the smallest. So we'll choose this as our next source, 4, 6. Let's update the distance. The adjacent vertices of 4 is 5 and 8. For 5, the distance will be 6 plus 1 equals to 7. So 5 plus 7. And for 8, the new distance will be 6 plus 7 equals to 13, which is actually greater than 7. So we'll not be updating the distance. 3, 12. 6, 11, 8, 7. New source will be 5, 7. So the adjacent vertex is only 6. So for 6, new distance will be 7 plus 2 is equal to 9, which is smaller than 11. So 6, 9, 3, 12, 8, 7. 8, 7, we forgot to change the distance. Let's update it. So for 8, 7 is going to be the new source. Let's update the distance of 8 as well. 6, 9, 3, 12. Between these two, 6, 9 is smaller. So our next source is going to be 6, 9. Let's update the distance. And from 6 vertex, we can go to the 7 vertex. So the distance of 7 is going to be 19 and 3, 12. 3, 12 is smaller, so our new source will be 3, 12. Let's update the distance. 12. And for 7, the distance would be 12 plus 9 equals to 21, which is greater than 19. So we'll not update the value 7, 19. Since this is the only vertex left, we'll choose this our next source. So 7, 19. So let's update the distance 7, 19. Since the list of visited vertices is empty, meaning we have found out all the shortest path possible from the source to all other vertices, and those distances are stored in the dist array. So this concludes our Dijkstra algorithm.